types of polymorphism. Now, as I told earlier, we discussed this in first unit that there are two types of binding uh, that are done. Binding of the function. When I call any function from my main function, like add is being called, the object, I won't say the object because at times we can even use pointer to call the function. So I'll say that the calling entity which is present, let us suppose there's an object O and I'm calling it with the object O. Whatever is the calling entity, the type of that calling entity is inquired, and if that object O belongs to class A, then this add function is searched for in the class A. Now, at the compile time itself, it is decided that which add function should get executed. The add function which is present outside class A, or the add function which is the member function of class A. Because we have a clear cut understanding of what is the calling entity and what is the type of my calling entity. Clear? So when this decision of binding any function call with any of the classes, when this is determined at compile time, we call it as static binding or compile time binding, or even we call it as early binding. Early binding. And when this decision of which function should get executed is delayed till the runtime, then in that case, uh, that binding takes place at runtime, I mean, then that is called as dynamic binding or runtime binding or late binding. Because the decision of binding is being taken late, it is delayed till the runtime. Got it? Okay, now we are clear with the concept why we are focusing on this binding. There are certain scenarios in which early binding fails us to give the desired output. At, in those situations, we expect the binding to take place at the runtime, simply because otherwise we would get the wrong output. Right? So we'll discuss that scenario also. Okay. Now, how do we? Yeah, we know that memory is allocated at compile time, and in case of runtime polymorphism, the memory is allocated dynamically. Fine. Now, the two ways in which we are implementing the static polymorphism or compile time polymorphism in C++, the two ways we implement this is either by using function overloading, or by using operator overloading. Okay, we saw there can be multiple meanings for operators and there can be multiple meanings for functions. Functions or methods, terms are used interchangeably. So we can denote functions with the term as method also. Clear? Whereas if we come down to dynamic polymorphism or runtime polymorphism, then there are two, or I would say three features of C++ that are involved in implementing runtime polymorphism. Number one, there should be an overriding scenario or inheritance scenario. Number two, pointer feature is required. And number three, virtual functions are required. Right? By a culmination of all these three concepts, we are able to implement runtime polymorphism in C++ language. Okay, fine. We'll come to this part, but as the syllabus prescribes, we'll have to firstly discuss about what's operator overloading, method overloading we already have discussed in unit 1. Operator overloading we have to formally cover. Quickly we'll cover that and then we'll go for runtime polymorphism. So two functions with same name but different number and type of arguments is called as overloading of functions, and based upon how many parameters we are passing during the function call, the call to the appropriate function is determined at that time. Right? So here we are having the same sum function with two parameters and the other sum function with three parameters, and it's returning the sum of the parameters. So we are calling the function by passing two parameters over here and then passing three parameters over here. Depending upon the type, the number of parameters that we are passing, the appropriate function would get executed. Right? So this is common compile time polymorphism. Why we are focusing on this particular part, that which sum should get executed, that body is bound with the function call at compile time. Understood? That is why it is called as compile time polymorphism. Okay. Now from here, the runtime polymorphism topic starts. Let us see that. Now we will see a brief introduction about what function overriding is, then we'll see operator overloading and then runtime polymorphism. Okay. So function overriding, we can consider it as an example of runtime polymorphism. And what is function overriding? We have just now seen when a child class declares a method which is already present in my parent class, then such function is called as overriding function. Right? So here we have a disp function in my base class A, and I have a disp function with similar argument list, that is empty argument list, in my derived class B. Naturally, if I give a call to the object of class, to the function with the object of class B, I'll see that the derived class this function is getting executed. Okay, fine. So function overriding is usually used to achieve runtime polymorphism. Now, as we discussed, if the call to the appropriate function is determined at runtime to decide which definition amongst the two function definitions is to be called, then that is called as runtime polymorphism. Okay. I would quickly brief you on this before we go for, if we start with operator overloading, it will be too big a topic to cover. Let us firstly discuss about how function overriding can be used to implement runtime polymorphism. Okay, so I have a class A as usual, and I have a class B inherited from class A, and suppose I had a display function and a display function which is overriding the base class function. In my main, If I try to create object of class B and I say disp, naturally we know that the the overriding function, that is class B function, would get called. I'll write here B, so that class B function is called and whatever is the body that will get executed. Fine. Now, if I have I'll take a pointer of A type, and if I say I'll take a pointer and I'll take an object also. Now, if I say P is equal to address of A, then I say P arrow disp, which function will get executed? Hmm?
Base class.
Base class, that is A class, right? Because again, what we are saying, we are observing, the type of the calling entity. Now, what is the calling entity over here? Pointer P is my calling entity. What is the type of P? It is A. That is why this binding is done at compile time, and this function of class A will get executed. Now, observe this very carefully now. If I use P to hold the address of class object of class B, can I do so?
Yes.
Yes. We saw the rule that a base class pointer can hold the address of a derived class object. So B is object of which class? Derived class. So can it be, can its address be held in the pointer P? Yes, this is possible. But the other way is not possible. Huh? So if I create a pointer of class B, say suppose Q, and I say Q is equal to address of A object. So this is not possible. Okay, remember, base class pointer can hold address of its descendant classes. Means if I even derive class C out of class B, then also class A pointer can hold the address of class C. Right? All the descendant objects address P can hold. Okay. Now if I say P arrow disp, what should be the output? Yes.
P. Derived class.
Derived class should be executed. You are absolutely right. Derived class dysfunction should get executed, but it should get executed. It does not get executed. Ideally, it should be executed, but it executes this. Why? What is the calling entity? P. What is the type of P? A. So it searches for dysfunction in A and it executes this version of disp function, which is absolutely wrong, isn't it? We wanted disp function of B class to get executed, but actually what happened, due to compile time binding, compile time binding of function with the class A disp function got executed. Problem, right? So what to do? How to solve this? This binding, which is happening at compile time, we somehow want to delay that binding. It should not happen. This binding decision should be delayed till the object B is created and its address is assigned to P. Now, once P holds the address of object B, definitely dysfunction of class B will get executed. So we want to delay this particular decision. Now how to delay this particular decision? Simply when at compile time, this function is getting bound to class A. I mean, the function call is getting bound with class A. We will put a keyword virtual over here. What it will say that if the compiler sees the disp function in class A, along with that, it also sees it's a virtual function. Now with the keyword virtual, compiler understands that this binding has not to be done at compile time. It is left to be done at the runtime. Right? Now, if we execute this code, you will see the output is, I mean, whatever you display in the class B version, you will see that version of disp function is getting executed because the binding did not take place at compile time. Is it clear? We'll see the demonstrations, we'll see the variations, in which cases it is possible, in which cases it is not possible. But I hope you all got the reason why runtime polymorphism or runtime binding is necessary.